Dear members of the European Academy of Sciences and Arts, it's again my pleasure to welcome you to this remarkable event. My thanks again to the two deans of the Art and Medicine classes, Violeta Dinescu and Dušan Šuput, for organizing this evening. Tonight is again about music and mathematics. We know from many lectures in this series how closely these topics have been linked since ancient times. Since the Pythagoreans, geometry, arithmetic, astronomy, and music have been counted among the so-called exact, that means mathematical sciences, in Latin, the quadrivium. According to the Pythagorean view, all four disciplines are concerned with the proportions of quantities. What is the proportion between a quantity A and a quantity B? The quantities can be distances and areas as in geometry, numbers as in arithmetic, celestial spheres as in ancient astronomy, or tones as in music. According to Eudoxos of Knidos, an ingenious Greek mathematician in the antiquity, the harmony of the universe was determined by these proportions, which by no means have to be whole numbers, so-called integers. Today we speak of fractions or rational and even irrational numbers. This is why, for example, quarter tones or microtones in general are considered in music. And this is by no means only abstract mathematical theory. This evening's lecture will show how these tone ratios play a central role, for example, in Arabic, Turkish, and Persian music. The next lecture will also deal with the mathematics behind all natural phenomena. Modern natural science show how we have to deal with systems of varying complexity in nature. A liquid, for example, consists of many interacting atoms, a cell of interactions of many molecules, an organ such as the brain of many interacting cells, in this case nervous cells, or a big ecological system of many interacting organisms and populations. When these systems are open, that means that they're in exchange with substances or energy with their environment, they can be harmoniously balanced in equilibrium, fluctuating periodically, or become chaotic. This depends on the type of interaction between the elements at the micro level. If feedback is involved, this is also referred to as nonlinear interactions, which are difficult to predict. This evening's lecture will show that such complex nonlinear systems can become chaotic even when they are closed. That means when they are not exchanging matter and energy with their environment. The nonlinear equations that describe such states are, of course, not as simple, linear as the Pythagorean proportions which I mentioned in the beginning. However, they show that mathematical ordering are hidden behind even highly complex chaotic states in nature. The connection between arts and science is once again explained in an excellent way this evening in both lectures. I thank you for your attention.
Thank you, Klaus. It was a wonderful interaction. And now I'd like to present the first speaker, who is Professor Tassos Bountis, who's Professor Emeritus in the Department of Mathematics, University of Patras. And he was a professor there for 16 years, as well as director of the Center of Research and Application of Nonlinear Systems that we just heard about. In 2014, he was elected corresponding member of the Academy of Athens in the chair of complex systems. In 2015, he was elected member of the European Academy of Sciences and Arts in Salzburg, so he is our very valuable member. And he also received the Slavsky Award for outstanding scholars in nonlinear physics, physical science. He obtained his PhD degree in physics from the University of Rochester, New York, and that was in 1998. And he has taught at universities in the USA and many other countries like Brazil, New Zealand, Australia, South Korea, and so on. And his research has been supported by many universities and funds. And he was also involved in 30 Greek sub schools and 5 PhD schools on nonlinear dynamics and complexity. Authored 7 books in Greek and 1 in English in complex Hamiltonian dynamics. And he has supervised more than 20 theses.
Yes. Would you want me to continue? Fine. This is good.
I think it's a problem with with the voice. So please.
He said the most important things. Okay.
Yeah.
Now, that was a great introduction by Klaus that put the whole topic in focus. And I am happy to accept Violeta's invitation. She twisted my arm. She said, you have to come in at this moment with a lecture. So I tried to collect some of the things not that I have done, but that are the foundations. I believe mathematical foundation, as Klaus pointed out, mathematics has to be at the basis of what we do. And from then on, I believe I can show you that we learn a lot about nature and the world around us. First by observation, and then by proceeding to look and try to see behind. Don't just watch what happens around. We have to look a little more carefully. Now, what I will tell you today is actually in a paper. I hope you saw this thing falling down here, that I just published in the proceedings of our academy, which is a very good idea. Ioannis Liridis had encouraged me to do this. So in this paper, actually, I have done a lot more than what I will tell you about today in the short time that we have before us. Now, what is complexity? Well, we're now in the beginning of the 21st century, and we must have understood something. One of the things we've understood is that complexity is a property of large systems and of huge number of units, but also small systems involving very few, but they have to be non-linearly interacting agents. And they can, even if they are few, they can exhibit chaotic or very complex behavior. So it's not a property only of large systems. Now, what happens with complexity is we have started to look closer to new structures that we see coming out of non-equilibrium. So we have something dynamic going on. Equilibrium is fine, and it's actually not interesting. It's static. Out of non-equilibrium, however, with some kind of reason behind it, we see structures appear. We see order coming out of chaos. From bad weather, we can all of a sudden see the sunshine coming out, and we have a sequence of order and chaos in our life. what we are interested in is nature is not proceeding randomly. Nature has something called self-organization. It knows us how to self-organize. Look at the different kind of species, animals, or how they organize together when they find a habitat they can feed on, and they avoid the enemy. There are all the time around us, there are certain dynamical evolutions and phenomena that we must try to understand. Nothing is random, really, but everything has behind it a certain reason. That's the reason we are trying to get into from the point of view of complex systems. Now, mathematics has been helpful so far. You've all heard about the theory of chaos, the unpredictable time evolution. It all started with small, low-dimensional systems. Great mathematicians did not attack 1,000 dimensions in a system. They started with very few. And even there, they realized there is this unpredictable chaotic time evolution at times. Now, today, we have gone to much larger systems like our bodies, biology, like the weather, and certainly functions in the body, which I will mention later. And of course, our friends, the engineers and physicists, are interested to learn about mechanical, chemical, and electrical oscillations, which they wouldn't like to be very chaotic. They would like to be able to control them. However, there is also seismic activity and even stock market fluctuations that one could indeed incorporate in what we call complex systems. And we have started to develop time series analysis and many other ideas to go with them. Now, as Klaus said, mathematics is behind what we do. And as the ancient Greeks did, geometry is one of the fundamental areas that we must learn in the high school and in our education. Now, there's a new geometry, as you have heard about, besides chaos, which is in time evolution. Fractals is complexity in space. So we see complex structures around us in the trees and even in our lungs, the cardiac muscle network, the blood circulatory system. They are all having a fractal nature. Why? Because they must break down into smaller and smaller pieces, which are very similar to each other. Take, for example, the blood in our veins. In order to reach the ends of our fingers, it has to break down, bifurcate into smaller and smaller channels until it finally comes out into little thin tubes that arrive for the blood to reach our fingers. The same thing happens with trees. For water to go up the trunk and into the leaves of the trees, they have to be smaller and smaller structures for this to happen. So as we will see, I believe everyone by now recognizes that we must learn to work with mathematical models. We may not all be mathematicians, but we must learn about modeling. And that's very important because the models will tell us what are the main features of a complex system. We don't want to know the details. And we will have insight to find more about their fundamental properties. Now, what are fundamental properties in complexity science? What have we learned? We have to use mathematics to observe, measure, understand complex phenomena in the natural sciences. These are the questions we need to address. Can we find universal principles and laws, not in just a simple observation of a tree and a leaf, but more generally? Can we generalize? Start with a simple picture and begin to understand what happens in the larger scale. And so we will see how we will find out more about our complex systems that are around us. Can we use then our own understanding, intuition, and perception to model what we see, to keep the most important factors in the system? And they will help us analyze. Forget the details. We want to know what is the central theme behind what we see around us in nature. So we look outside, but we don't observe. What I always tell my students is just don't look around, observe. What do you see at a tree? What do you see in a tree? What is it that impresses you? Did you think about the question, why do they go so high? Why can't they go higher? What's the reason for having this complexity? And let's look at it also on the level of a leaf. What do you see in this picture? I think many of you will notice, who have heard about self-similarity, that the distance between those bifurcations of the veins of the water on the leaf, you see, are not very different when you look at them along the big branch. This distance here is about, oh, excuse me, we have to go maybe one back here. All right. And as you see, when we take the central road, then take the other vein of the leaf, you will see here also there are bifurcations of little veins at distances that do not differ very much from each other. And later on, so we see there is a scale. Nature does not reproduce itself exactly. It reproduces its pictures in smaller and smaller spaces, wanting to fit. A tree cannot be 100 meters or 200 meters tall. Leaves cannot be huge. Everything must be contained in geometry, in nature. So we observe a kind of self-similarity. Now, take a look around at another complex object, which is a coral. How can a coral wrap itself around in this complicated form? How can it do it? It is necessary for it to do it. Just like a sponge must have hundreds and thousands of little holes so the water can go in, and so the sponge can absorb the nutrients from the water. So what does it have? Does it have volume? No. The volume of the sponge is very small. What does it have? Area. If you cut the sponge in small pieces, you will cover a tennis court if you stretch around. So what you see in a sponge is actually a big area folded together in a very, very wise way, which since the creation developed to be of that form. So now mathematicians think, is it possible to make these things ourselves? Toys at home. Mathematicians like to play and create toys at their home that can reproduce the main features of objects that they see around. Peano, these names are very familiar, I think, to many of you, and they go together with important theorems in mathematics. What do? They saw that there is an amazing way that if I take a curve that you see here on the left, and I reproduce it in the same shape, but in smaller scale, then you get this curve right here. If I repeat this, look at this picture on the right, it is a replica of the previous one, but in 4 different places. And now if you do this again, you will make every square of this gamma figure just like itself. So by doing it this way, you are filling out a square. So the big question arises, where does this curve live? Is it one-dimensional? But how can a one-dimensional object cover a 2-dimensional surface? So where does it live? Well, we were fools not to recognize for hundreds of years that dimensions do not have to be integers. Something is hidden between dimension 0 and dimension 1. Something is hidden between dimension 1 and dimension 2. And now we are beginning to understand it. This is complexity in space. Well, you say, but there are practical questions. Can you reproduce that coral for me, please? Yes, I can. Oh, now it's easy. I can go to higher dimensions. I can give you this object. You still don't like it because it has a lot of corners. But then you have a friend who is a master of computer graphics, and he can take this that you give him and just smoothen the corners. And there you have a coral. So we are beginning to learn how to reproduce figures and pictures we see around us. Now, let's summarize and see, what did we see in the previous models? We saw that there was a similarity. We began with an initial figure, we made copies of it in smaller and smaller scales, and we obtained something new, something that looked like a coral or a sponge, whatever, but it was certainly new and more complicated, complex, if you like, complicated, spatially complicated. Now this must somehow be studied, because we're coming up to I think one of the most important laws of complexity. And the law is the law of self-similarity. Self-similarity under scaling is an observation, if you like, a principle, a law by now, that we observe in many, many things we see around us. If you see a big wave in the sea, haven't you observed all the little waves that follow it wherever it goes? In the famous Japanese pictures of a wave in the ocean. But you've seen it, you know these things. So nature around us is self-similar. It reproduces the same picture in smaller scale, and it challenges us to understand it. So now, how do we understand it? Is it perhaps this way that we understand that nature cannot fit large size objects in very limited spaces and have just one size? Try to fill your house with boxes. You cannot, unless you make the boxes smaller and smaller and smaller. So if you want to fit large size objects, you cannot do it unless you have a law to follow. And so we will come back to this behind. And now we want to understand this self-similarity under scaling. Understand the complex structures that we see around us. I will begin with the famous mathematician D.R. Cantor, who sat one day in his office and thought about it. He just drew a straight line. And he says that I have here, just with a blue color to show you where it is. It is still one line of this length here, say 1. And he said, well, let me remove its middle third. And then remove the middle third and the middle third. And continue doing this until there are no segments anymore. It's all points. It has to be points at the end. And the question is, what are we left with? The answer is, we started with 1 dimension, as we did before, and now we are down to 0 dimensions. No. The object you see below, all these dots that remain, are actually as many in cardinality, as many as there were in the original single segment 0 to 1. That's when Cantor says, I don't believe it, but it must be true. How can all the points, if you count them in the top line, be the same in number as the ones that are left in the end? This must be, it cannot be the same dimension anymore, and it's a dimension that is between. So we discover right now new worlds between dimension 0 and dimension 1, between dimension 1 and dimension 2, for example. Well, let's start to add lines to a beach. Suppose we want to go to a beach and we have little rocks here and there, triangular rocks, and we begin to see the beach. And you know, real beaches are like that. They have little inlets and little rocks all around it. Continue doing this to very, very small size. What do you think you will find? The end curve that you see here down, it says at the 4th step, the length of this curve, if you measure it, is infinite. You see it before you. If you want to think it's a 1 dimension, well, it's not. It has to be more than 1 dimension. Otherwise, it couldn't be infinite in length. And now we discover there is a new world between dimension 1 and dimension 2. It is greater than 1, but smaller than 2. And that, of course, can be calculated mathematically, as I will show you in only one slide. So there we are, we have that. Now, what about subtracting? We begin with a triangle, and now we subtract the middle triangle. Then we subtract all the mid triangles. Now we are moving from dimension 2, the triangle was, to a set of triangles that make all of this. We're going down the dimensions now. But in this way, we are getting the famous Sierpinski gasket by the famous Polish mathematician Sierpinski, which lives in a world between 1 and 2 dimensions. But you see now the dimension is more than it was before. When we climbed out from 1 dimension to 2, we found 1.2, what was it? And now we're going from 2 dimensions down. Now this is more dense, it seems, than the previous one. So we are beginning to build an intuition about what the different dimensions mean in between. That's the only way we can describe sponges, corals, fractals. There is no other way. We have to admit that there are other dimensions between the integer ones. And we need a new kind of geometry called fractal geometry. When I first heard Mandelbrot speak, The room was full in 1977, and I was in Rochester, New York, in a conference, and I heard people telling near me saying, "This guy is mad. It's definitely, he's crazy. The way he speaks of what are these fractals, what is?" That was 1977. Now we know a lot better than that. So just a slide for some of you who are mathematically inclined to see how we do this kind of computation of dimensions. You see, what you have to do is break down your object in many, many little squares, count only the squares that are blue in the blue region, because this is the kind of shape you want to study. Keep doing this at smaller and smaller triangles. And finally, you will see that if you assume that what you're looking under your microscope, let's say, it's a microscope. So what you see at this object must be measure m. The number of the squares goes to infinity, and it's raised to a power d, which is the dimension. Now, if d came out to be 2, we would say, well, there's no fractals, everything is integer, no worries. And that comes out sometimes. Yes, d may be equal to 2. But in the shapes we study here, d is not equal to 2. And it's calculated like this and comes out to be 1.2, 2.2, whatever you like. Now, this was all complexity in space. Let's look a little bit about complexity in time. And without knowing anything about complexity in space, Henri Poincaré, who was a great savant of the end of the 19th century, mathematician, physicist, philosopher, you name it, you should all read some of his works and more philosophical works. The one who actually studied it from the point of view of the stability of the Earth, Sun, and Moon system. And he found out that the system is not stable, it may be stable, but it has regions I cannot enter, said Poincaré, because you won't believe it. The solutions go away from each other in a chaotic way. He didn't say the word chaos exactly, but he did notice for the first time that motion and dynamics can be extremely complicated. Now, let me take, for all of us here who like biology also, the problem of evolution of a population of rabbits on an island. Now, I will take x of n to be the ratio. How many rabbits you have in an island at the generation n, divided by the total number n that the island can support. Okay, then you have a fraction you want to study. And you see, mathematics gives you, again, an equation. The equation says, well, the result of the next generation is proportional to how many little rabbits they give birth to. That is the advancement of the population by birth. But there are rabbits that die. So I must subtract x squared from here. So I have a term that talks about births and a term that talks about deaths. And they two have to come to some equilibrium. It's a dynamical equilibrium. What is the R? R is the number of rabbits that a rabbit-laid mama gives birth to. A very, very biological parameter. If the rabbits population increase rapidly, however, you know what will happen. The food on the island will disappear and everybody will die. So the rabbits have to come to some kind of equilibrium in time to survive. And that's exactly what happens. Now, if you look at this picture, it does remind you of a tree, doesn't it? If you look a little bit sideways. So you see pictures of trees and branches are all over. And here, this is dynamics. Now, this is not geometry, huh? But geometry and dynamics are really sides of the same coin. You see it. When the rabbits populate in two generations, then they can oscillate between two numbers. One year you find 300 rabbits, the other year you find 200 rabbits, 300, 200, etc. But as the number of rabbits increase and the mama of rabbit gives birth to more rabbits, then comes instability. Then there is chaos. Unpredictable behavior. You cannot measure how many rabbits there are on the island because you have crossed chaos. And this is a sequence of bifurcations. Once this solution was stable, then it became 4 branches, then more branches, and then we entered into chaos. Chaos is therefore, just like Poincaré would have said, unpredictability in time. You don't know how many rabbits will survive, how many will die, and it will be chaotic oscillations. But we learned a new word, bifurcation. As we see roads sometimes when you drive, there are 2 ways to go, and you have to be careful which one of the 2 ways to take. Well, bifurcation, in fact, is not such a bad idea and a new phenomenon. There was a fantastic experiment, I learned about it many years ago, where you put cockroaches in a dish here with 2 shelters. And the cockroaches, of course, want to avoid the light. So they're going to hide themselves in one of the shelters, where they don't fit in all the shelters. So what happens in the beginning, they split in 2. So half of the cockroaches go to the one, half to the other. As soon as you see here, as soon as the size of these shelters reaches the height where all of them can go into one, they all go into one. For some reason, we don't understand, and that has been experimentally verified. Why do I have 2 branches? You see the bifurcation. We were going along this line, and now we have 2 choices. Why? Because in one experiment, the cockroaches chose the one on the left. In the next experiment, they chose the one on the right. Nevertheless, the phenomenon was everybody wanted to be close to their friends. They didn't want to split, as long as there was room in one of the towers. Now, you may be surprised as I tell this, that all of this can be studied by these 2 differential equations. We don't want to discuss differential equations, but it's remarkable to me, and what I show to the students, how much can be understood by solving differential equations, elementary mathematics. This is difficult to solve. We have to go to the computer. Nevertheless, the scientists you see down here, Dinescu was the leader of the group, actually published this, all of this explanation by differential equations. That was back in 2006. So bifurcations are important phenomena. Now, you all have heard perhaps of the person who found out what chaos can be in differential equations. He was the one who said a butterfly flapping its wings in Peking can start a tornado in Texas. Why did he say that? Because there is chaotic behavior in the weather. And the differential equations you see now, I believe you must take my word for it now. You have started to see that differential equations are a good tool to study in mathematics. There are only 3. They should not be so difficult. And yet they produce a kind of object that is very difficult to analyze. And the reason is that I show it to you here under different projections. It starts from 3 dimensions. Now it looks like the 2 eyes, as if it are 2-dimensional. Is it 2-dimensional really? Did it go down to 2 dimensions? Not really. Then they wouldn't be chaotic. In fact, its dimension is a little more than 2. That's why you see them all falling like a plane, right? It turns around, but it still looks like a 2-dimensional surface. It's not. It's more than that. And it's only 3 equations that have to do with the weather. So, as you see, let's go back to geometry now. We see a tree, and what are we surprised about it? Yes, well, it's beautiful. It has a very nice shape. But why is it so tall? Why does it stop there? Why are the branches big here, smaller here? There are bifurcations, I can see. They're all following each other in a smaller scale. Maybe nature is giving instructions to the tree that cannot be doing everything at every point randomly. There has to be a plan in the seed. How does a tree grow? Starting from a seed. Where is all this information? There must be an algorithm in the seed which tells us by a self-similarity process for the tree to grow in that particular way. Now, mathematicians are quite ambitious, and they say, and also like to simplify things very much, and say, well, wait a minute, this looks like a tree. Well, why don't I make a model out of it? So every branch becomes half of it, and then half of half, and half of half, and there are bifurcations, all of this. Can I do this mathematically? Yes, you can. And you find something that's a very silly picture for a tree, but it's not so silly, really. if you follow it, the major points of nature we have been able to imitate in this very crude design right here. And now we are a little more daring, and we can go and build more sophisticated trees and plants, following Barnsley. And that was already in the 80s when he did this. And today, even in movies in Hollywood, they use this to make pictures with very, very small people attacking Troy. The armies are all reproduced, and the soldiers are like fractals designed to follow, or the faraway mountains are also following these laws. And the laws are simple. Okay, you don't see me. That's okay. We have to, Barnsley said, we need contracting transformations. We have to make everything shrink. And if you do it by certain law, then it will always lead to the same shape. It all depends on how you play around those steps you give to the algorithm. If you start, for example, putting squares like this, like a child would put boxes, but make the boxes smaller and smaller, what do you find in the end? Wow, this famous Sierpinski gasket is here. Now, don't put the boxes like this, says Barnsley. Move them around a little bit according to another law. Turn them around, but watch it. Follow the same law at every step. Take every picture. Do you see this picture here of the three boxes also reproduced here and here and here? Keep doing this, and then you come up with something that looks like an ivy tree on your house. It goes. So many things we can do. What other things can we do? Well, let me give you an example. I always tell to my students, and it's easy to try. Take a picture like this rectangle, could be a circle, doesn't matter. But take this object and repeat it 4 times. I break it into parallelogram 1, parallelogram 2, 3, and 4. Here is a small stem. It's a line. It's a very thin parallelogram. That's the rule. That's it. Now repeat this rule to this parallelogram, to this number 2, to 3, and to 4. Repeat this rule over and over again. You start with rectangle 1, the main leaf. You follow the rules. And what do you see at the end? This. We started with a law, we reproduced it at smaller and smaller scale, and we find something that looks like a fern tree or something. Barnsley's fern shown here. So that's how nature perhaps that's how nature works, to create all these beautiful pictures, starting by certain laws from the very beginning. Well, I don't want to take any more of your time. After all, this is supposed to be a short lecture, but I simply want to tell you that right now, today, complexity is growing so fast that besides the Nobel Prize about predicting the global warming of the Earth in 2021 for complexity, we already know from many years that physiology and the brain, especially the brain, that is actually our own purpose to study and understand deeper how our brain works. Differential equations can still help you. You can study the muscle contraction. You can study the way muscles work by using differential equations, the way blood flows and everything. And then comes a phenomenon that we should all be very interested in. It's called synchronization. Synchronization is really the key reason, the way the brain works. The brain works with different parts of it synchronizing with each other. No part of the brain can do everything. They all have to divide the labor between them. And that's what we find in brain-computer interface research. So complex networks, as they have applied in the brain, can understand features of epilepsy, distinguish them from Alzheimer's, and can even go down to study traffic motion in the streets, and even the way that vehicles should be driven automatically in real-life traffic. I will close by bringing to your attention, all of you should know very well the word synchronization. Again, another Greek word, as we were saying, Violeta. Synchronos means, and Klaus knows that also very well, I think, with his Greek knowledge. Synchronos is at the same time. Synchronos. the same time. So synchronization is the way the brain works. If you want one part of your brain to communicate with another, say now one part of your brain, as I'll show you a picture, here's a message. Another part of your brain says, tap your finger. These two parts of your brain must synchronize. It's not just a meaning of just a communication. It is synchronization. And Huygens, the famous physicist who studied wave motion and so many things 3 centuries ago, saw it in 2 clocks. 2 clocks were hanging on his wall, and they had very little communication, through a bar, and yet they synchronized. So it's the same thing like this. If you take now, we have an experiment. We see 5 metronomes, which when you leave them there, they have no reason to synchronize, right? So their oscillations diffuse on the table. They diffuse. Now let's put them on these supports. And you see something remarkable. Because of the same bar that joins them, after only a few minutes, they synchronize like this. And this is analogous to the idea that Huygens spoke about. So I'm finished by these pictures that show you that when you know the experiment that some psychologists use, they tell you to do something, doctors, and you tap your finger. I tell you when you tap your finger, and you start tapping your finger. Well, you hear my message, you tap your finger. This means that your auditory cortex must hear my words, and your premotor cortex and your sensory motor cortex must tell your finger to tap. So these areas in your brain must communicate for the message to pass across. How does this inner voice work? Only with synchronization. That makes these areas synchronize and have the ability to communicate with each other. If they cannot synchronize, then you may have a very serious disease and you cannot tap your finger. I will tell you, and you will not be able to do it. So anyway, these are my conclusions for today. The science of complexity, we call it a science. Well, yes, because it offers us a methodology that seems to unify the different aspects of nature and sometimes different functions that we see in living systems. They seem to synchronizing and so on. And there is something that is larger than the sum of its parts. This is the way to define complexity. Something is complex when the object is bigger than the sum of its parts. You put the parts together and all of a sudden the car begins to move. That's not so easy. If you put all these parts together in a pile, the car will not move. So you have to put things together in a way that is complex. And unless you use mathematics and computer science now, of course, I would add, not only theoretical mathematics, you will not understand the language of nature around us, and maybe other parts of nature, and our human nature even, our psychology. And we have new concepts, new models and experimental techniques, and I believe for students it's an ideal direction to proceed in their life, to learn, because they will learn many sciences before they finally choose their own specialization. Thank you very much for listening.
Thank you very much. It's extremely interesting lecture. I already have a few questions, but first we have to hear the next speaker, and Violeta, please make presentation, introduction.
I will leave my...
Thank you very much for the fascinating presentation.
Showing my camera because I'm just coming from Olympus, which is which was also a bit chaotic and non-linear.
But you have to share your screen.
Thank you so much for this fascinating presentation, inspiring. Thank you.
Good.
I would now like to present and invite Aziz Ifzarne. He is a professor of mathematics at the National School of Applied Sciences in Coribda, part of Sultan Maurice Seyman University in Morocco. He holds a PhD in mathematics from Mohammed University in Rabat, as well as a postgraduate diploma in computer engineering from the Faculty of Science and Technology in Tangler. In addition to his academic work, he is an active researcher at the intersection of mathematics and music, with numerous publications in international mathematics journals. His interdisciplinary interests extend into musical composition, and several of his works are preserved in the archives of the Moroccan National Radio and Television Company. Aziz Ifzarne received classical music training also at the Rabat Conservatory, studying also piano, and was formerly a member of the Rabat Choir. He is also the creator of YouTube series dedicated to exploring the deep connections between music and mathematics. He is also the author of 3 books covering diverse topics and continues to contribute to both the scientific and artistic communities through his unique interdisciplinary approach. Aziz, you have now the floor, please.
Yeah, thank you, Violeta, for this beautiful introduction, and I thank you thank you, Tassos, for this fascinating presentation. I need first to share my presentation. Can you see the slide?
Yeah, it's perfect.
Good. So, hello, it's a pleasure to participate in this wonderful colloquium, Arts Meet Science. It's so true, arts really meet science. I'd like to thank the organizing committee and especially Violeta for inviting me. Thank you, Klaus, for the beautiful introduction. So as the title indicates, the subject of this presentation, it's about exploring a quarter tone based on harmonic series and its impact on Makam music. This research was published at the 9th International Conference of Mathematics and Computation in Music, which held place in last year in the historical city Coimbra in Portugal. About 20 years ago, my interest in the relationship between math and music began. And 6 years ago, I started making videos about this relationship. To my knowledge, those are the only videos that talk about this topic for Arabic speakers. So let's start with a brief overview about quarter tone music. Sorry, Okay. In Western music, the most common tuning system is the 12-tone equal temperament, denoted by 12 teeth. In this tuning system, the octave is divided into 12 equidistant steps. That's what we see, for example, in the piano. So in this tuning system, the smallest step is half tone, also called semitone, being exactly 100 cents. Quarter tone music is a different approach, where the smallest step is not half tone, but quarter tone. In the 24-tone equal temperament, the octave is divided into 24 equidistant tones, and the quarter tone being exactly 50 cents. For example, if we take those two pitches, D sharp and E, the note between them it's what we call E half flat, And the interval between D sharp and E half flat, it's quarter tone. Same thing between E half flat and E. It's important to remark that 24-tone equal temperament includes 12-tone equal temperaments, and this gives a possibility to musicians the possibility of using the additional pitches without losing, sorry. Yeah, without sacrificing the techniques available in 12-tone equal temperaments. If you want to represent all the 24 notes of this tuning system, we need, of course, we need additional signs of alteration. There are in literature, there are many different notations, but the quite common notation is this one. Half sharp or plus raises a note by quarter tone, and half flat is denoted like this, or minus lowers by a quarter tone. So the chromatic quarter tone scale can be represented like this. Let's listen to this chromatic quarter tone scale. It can be interesting. Yeah. Oh, and the fundamental. Oh. During the 20th century, several musicians have made compositions for quarter tone music. In particular, we can mention Winiarski, Charles Ives, Alois Abba, and Don Ellis. To get a clear idea about this kind of music, let's listen to a piece taken from the 24 preludes, for two pianos in quarter tones, that was composed in 1934 by the Russian composer Winiarski, who lived for most of his life in Paris, and he contributes to construct a piano with a quarter tone, as you see in the picture. So let's see how it sounds.
We can't hear very well.
Okay. It's
we
not clear.
shall put your presentation anyway in the EASA internet page, so you have the possibility to bring recording in the internet.
Okay, of course.
Thank you.
So the sound was not clear. Yeah.
I'm sorry, did you press
I
the
can-
share sound when you were sharing your screen on Zoom? So when you shared your screen on Zoom, if you press
Yeah.
share sound button, it should work.
Yeah, Ipsum. I don't know where can I find this?
You have to unshare your screen, Bountis, and then do that again. You will see the share sound button.
Okay.
And then if you click on share on Zoom, then you probably will see share sound too.
Share on Zoom. Yeah. Yeah, share audio. Yeah. Okay. Let's try again. No? Great. Yeah, so it might be gerund and dissonant, but this initial discomfort usually disappears after a moment of listening. In YouTube, I remarked that some comments of confirm the same thing. Quarter tones can be also used to enrich the harmony by adding intermediate notes. This technique was, for example, used by the musician Jacob Collier. Let's listen. Yeah. The music genre where we find most quarter tones is Makam music. Makam music is widely practiced in several regions of the world. It is prevalent in Arabic music, in Turkish music, and Persian music. Of course, there are other regions in the world that use quarter tone music. In Persian music, Makam is called datsga. And what is makam? It's a heptatonic scale with, in general, with 5 pitches. And some makams contain, some makams use just the 12-tone equal temperaments, and other makams use, they use other intervals that contain quarter tones. To get clear idea, let's listen, for example, to C major. We are used with. Yeah, those are the white pitches in piano. Now C minor. Okay, if you remark here in C major, the interval between C and E, it's the major third, okay? And in C minor, it's between C and E flat, it's the minor third. So between E flat and E, there is an intermediate note, which is called E half flat. So we will listen to this note, and the makam that we will the result is what we call makam rast. Let's listen. So in makam rast, as I said, we replace E by E half flat, and we replace B but by B half flat. So here the intervals become between B and E half flat. The interval is 3 quarter tones, and the same thing between E half flat and E. Let's listen. Something different. As an example, I will make you listen to an extract of a song that I composed on Rust on G, transposed on G. Yeah, so in this makam you will find the neutral third. The neutral third is between C and E half flat, so it's something different. In the last Congress, someone told me it looks like belly dancers music. So now let's move on to quarter tones and overtones. The link between them. So overtones are also called harmonics or partials. We talk about supplementary frequencies generated along the fundamental frequency when a musical note is produced. So as soon as a tone sounds, overtones vibrate. And so overtones come directly from the rules of nature. And harmonics frequencies are numerical integer multiples of the fundamental. For example, if I take the fifth harmonic, its frequency is 5 times the frequency of the fundamental. Harmonics are very important in music theory because they provide pure intervals. For example, the second harmonic provides the octave. The third harmonic provides the perfect fifth, and the fifth harmonic provides the major third. And you know that in Western music, those intervals, the three intervals, are perhaps the most important. There is an interesting fact. It's that the 11th harmonic provides an excellent approximation of a quarter tone interval. And the interval in question is what we call the major fourth. The major fourth is it's the perfect fourth plus 1 quarter tone. Being exactly approximately 551 cents. We can find it, for example, between C and F half sharp. Let's listen to this interval, C, F half sharp. Yeah, again. Yeah, so this interval is linked to the 11th harmonic that we can find in nature. To visualize the situation, we can take spectrums showing the sound produced by playing, for example, the note C3 on piano, whose frequency is 130 hertz. So this is the note. So the fundamental that you heard, that we can hear, is this one, and 2, 3, and so forth. Those are the harmonics. And as you can see here, we have the 11th harmonic. Okay, so normally the 11th harmonic is F half sharp. If we return to the past, to Pythagoras, we know that the Pythagorean tuning was based on the perfect fifth, whose ratio is 3/2, and it corresponds to the third harmonic. So if we use the circle of fifths, this enables us the construction of the 12 notes in the chromatic scales. But the problem is that the circle of fifths is unable to close the circle by an excess of about 23 cents. That's what we call Pythagorean comma. It's the difference between 12 perfect fifths and 7 octaves. Now, what about quarter tone music? The question is how to identify the intervals for which the corresponding circles surround all 24 notes. The problem is that the perfect the interval of the fifth, it doesn't surround all the 24 notes. It surrounds just 12 notes. So identifying the circles that surround the 24 notes, this problem can be resolved mathematically by searching the generators of the additive group Z over 24Z. It is well known that A bar is generator of Z over 24Z if and only if A is relatively prime to 24. We get all the generators, all the possible generators. There are 8. Those are the generators. So the last 4 numbers in the right, they are the inverse of they are the inverse of the circles derived from the first 4 numbers. And if we exclude 1, because that represents the circle of quarter tones, so the remaining numbers, which are 5, 7, and 11, they are the most interesting. And the last one, which is 11, remains the most important because it's related to the 11th harmonic. So the last one is yeah, it provides the major fourth, which is related to the 11th harmonic. And we get the circle of major fourths. So the circle of major fourths, its advantage is that it surrounds all the 24 notes that we find in quarter tone music. And this fact was noticed by Winigrodzki in his book Manual of Quarter Tone. So this tuning system will be designated as 11th harmonic tuning or circle of major fourth tuning. So the major fourth, its ratio is 11/8, and it corresponds to the 11th harmonic. In this case, if we calculate the comma, it's the difference between 24 major fourths and 11 octaves. It's almost 32 cents. If we know that the Pythagorean comma is about 23 cents, so the difference between those two commas, it's about 9 cents. In this table, we have a comparison of the 11th harmonic tuning, 24 tone equal temperament, and just scale. Just small remark for just scale. How did we calculate those ratios? Because here we have rationals. They are obtained from using suitable continued fractions. At the end, let's see some applications of this tuning system to Makam music. Okay, in Makam music, especially in Arabic music, it is considered that Rast is the most important Makam. So can we find this interval, which is the major fourth in this Makam Rast? Yes, it's between E half flat and A. Between E half flat and A, this is major fourth. Also, another Makam which is very important, Bayati, we can find the major fourth between B flat and E, between B flat and A. Between B flat and E half flat. Yeah, between B flat and A half flat. And Saba, the same thing. So let's start with the Makam Rast. The second row, this one, indicates the difference in cents between the 11th harmonic tuning and the 24 tone equal temperaments. Let's listen to this Makam Rast, but not in 24 tone equal temperaments, but in the 11th harmonic tuning, which is more linked to nature, to harmonics. Yeah. Now let's listen to the same Makam through Moroccan dance called Atlas dance. Yeah. Now let's see another Makam, Bayati, using the same tuning system, 11th harmonic tuning. Yeah. Now let's listen to Bayati Makam through a Moroccan song called Marsun al-Hub, which means love messenger. Yeah, and last Makam, Saba. Saba is often considered as the saddest Makam in Arabic music, so please don't cry. Let's listen to Saba Makam. let's listen to this makam through a song. This song is called هو صحيح الهوى غلاب, which means is it true that love is the winner? It was performed by the famous Egyptian singer Kulthum. So as at the end, as a conclusion, we can say that 24-tone equal temperament, it's sure that it remains the most practical tuning system due to its numerous advantages. And perhaps the most important advantage of the 24-tone equal temperament, like the 12 teeth, is that it gives us the freedom to transpose, but any other tuning system, transposition becomes limited. But the idea of investigating tuning system based on natural harmonics remains exciting and holds symbolic significance. At least we know that quarter-tone music, as other kinds of music, has roots in nature. Thank you very much.
Wonderful. Thank you, Aziz. We became very curious now to listen more of your music. Applause.
Thank you.
Now we open the discussion, and I would be very happy if you could, Klaus, thank you very much, please. Unmute yourself, please. Unmute.
Okay. Thank you very much for both talks, of course. And I have a short question to the last speaker. You nicely described these different approaches in Western music and Arabic and Persian music with the quarter tones scaling. Now my question is, have you any idea why in these different cultures, these different, let me say, physically scaling in tones have emerged? Because it seems to be historically they have a similar origin. For example, the Pythagorean tradition, but why did they develop in a different direction? It's amazing, at least for me, the Persian and Arabic music also sounds rather familiar to me, and in some sense harmonious. So I'm not restricted to the Western tradition. But anyway, my question again: do you have any idea why there is intercultural this different development?
Yeah, thank you, Klaus, for your interesting question. I think that, yeah, of course, there was through history there was an exchange of music and cultures. For example, during the Ottoman period, you know that some Arabic countries like Egypt were occupied by Turkish, and so there was an exchange between Turkish music and Arabic music. Also, Persian music. The proof is that even some names of makams are Persian or Turkish, even in Arabic music. So that proves that there is a real exchange of music and cultures. But there are some differences about the way we play quarter tones, how we play makams. For example, in Arabic music, makam rast, if you take the E half flat, which is the most important pitch in this makam, E half flat, as it is played in some Arabic countries like Egypt, it's different slightly different from the E flat, E half flat, like it's played in Turkish or Persian music. In general, we say that the Persian quarter tone is slightly less than the Arabic quarter tone, and the Arabic quarter tone is slightly less than the Turkish. So the Turkish one is the stronger. Yeah. And even in the same country, we can find different ways to play those quarter tones. That's why some theorists, they reject the 24-tone equal temperament, because for them, we need to take in consideration the ways we play those makams. So the 24-tone equal temperament is that, like if we give the one way, but there are different ways. There are different, E half flats can be played, in different ways, not just not just one way. Yeah.
Thank you.
Thank
So
you.
beginning of a new research, a very good questions. Thank you very much.
You're
So
welcome.
I see now Peter Hermann and also Dušan. Please, I saw first Peter Hermann and then Dušan, I think. Peter?
Well, I think Dušan was first.
Yeah, okay, then
Well,
Dušan.
Peter, you can go on. You can be first. I don't mind.
Okay.
I can.
Okay. I don't want to question this analysis. I think it's actually very interesting to see the connection with mathematics and stuff. I want to have your opinion on a kind of contradiction I see. Quoting Livaneli Kadesimin Hikayesi, a book where he quotes an engineer. I just have to get this. Since we engineers don't see a building as just individual parts, but rather as a large whole that results from an overall plan with all its supporting pillars and structural calculations, my worthless essay entitled The Virtue of Forgetting fulfilled at least one function, because in addition to developing new ideas, it was also important to establish a connection between the existing elements. So my question where I wanted to have both your opinions is actually, you have on the one hand an analytical tool where you can strictly determine certain rules, rational rules, in terms of mathematical rules and numbers and so on. But at the same time, there is this overall connection and in a way it links to the previous question, where we cannot really understand what is going on, where it's about empathy, where it's about feeling, where it's about deeper things that are actually linked as well to different cultures. How would you, or do you have an opinion on this, what I see as a certain tension between rationality and, if you want, irrationality?
Yeah. Of course, music it's a sign. It's a science. It's rational, and also it's an art. So it's something very emotional. This is debate between from the period of Pythagoras. Pythagoras considers that music is related to ratios. Simple ratios, but we have also Aristogzenes, which considers that music we don't have to link music with mathematics, because for him it's based on the listening, on the emotion, and not on the mathematical calculations. So it's really a debate subjects. But I think that nowadays the music we hear, most of it's based on what we call the equal temperament in Western music, or even non-Western music. So in some Arabic words, in North Africa, we use 24-tone equal temperaments. Even there is no consensus about this tuning system, but in practice, it is, yeah, it is here. So this tuning system, it's based on mathematical calculations. It's irrational values. Huh? I think that, yeah, it's very interesting, yeah, debate. I don't have answer, but yeah, very interesting.
Thank you very much. And now Dušan.
Yes, can you hear me?
Yes, we can hear you. We do not see you, but we hear you. But now it's no more possible. So please, can you try again?
I have
Now it's
Tassos.
good.
It was very, very interesting what you showed about physiology. And it is a bit confusing for somebody who's not mathematician to see that there are two principles going on at the same time. Let's say you show that brain should somehow synchronize to exert an action, let's say finger tapping. But on the other hand, if the brain is synchronized, you get epileptic. So if it must be synchronized only on a very, very small scale. Otherwise, it's terrible. And it's the same true for cardiology. Of course, if you want to have the heart beating, all muscles must be synchronized. But if the rhythm is not random, this happens just before myocardial infarction. So there should be maybe two principles going at the same time. One type of dynamics making some wonders in synchronization, and the other one to prevent that. In brain, it's quite simple because when it starts, immediately the activated neurons get suppressed by inhibitory neurons around the focus. So what do you think from mathematical principles? How could you explain that?
I think your question is addressed to me about
yes.
And first, okay, I wanted to make a point that also one of the listeners here, Annette, wrote to me. There is a similarity between what I said and what the current speaker talked about. And the similarity starts from the point of view that where he played just a sequence of notes, 4, 5, 6, 7, just for us to see what is the basic background that he wants to build. And from then on, by combining this 5, 6, 7, 8 notes in a complex way, we arrive at something that musicians play, which appeals to our aesthetics. This is what happens also in the brain, in nature, in many, many other ways. So I was very interested in what the speaker said about the way Pythagorean structures or different combinations of notes can build into a whole which is very, very pleasing, aesthetically pleasing, or maybe not, if the combination is not. So indeed, there is some common ground between my talk and the one that the speaker talked about. It shows you that why we are in an Academy of Sciences and Arts, and why this series of lectures addresses both sciences and arts. Indeed, of course, one cannot extrapolate and say that, for example, in knowing about complexity and scales, we can be musicians. It is not so easy. And also, when we see certain functions of the brain doing simple tasks, as the finger tapping I showed, again, it's a very, very simple example. What happens with more serious situations, like Alzheimer's or epilepsy, is it's a lot more complicated. Synchronization is not a simple thing. So what happens in the brain is certainly very, very, very complex. We identify the principle of synchronization, and that is a way by which we can even interfere and make a person who has Alzheimer's and who has kinetic problems by desynchronizing the brain. There can be an intervention in the brain by which the synchronization breaks down, and then you see that person being able to move and function with his hand in any way he or she likes, but only for a little while. After we stop this, then the person goes back to the ailment of Alzheimer's or that prevents him from achieving something. So yes, we have made progress, but it's still far, far more complex than we think. The brain is by far not simple, and we don't understand it yet because there is something else also that's called the subconscious. We have learned in recent books, actually, that the subconscious plays a very, very important part, but in a way that we simply don't understand it yet. Look at how your dreams develop. In the morning, you try to make sense of your dreams. They were your dreams. You saw them. They are related to your life somehow. You should know what you have seen, but it is not so simple. We try to put the dream together to say what we saw and why did we see it that way, and it's still not easy because it was the subconscious working. So I would be very modest in saying that we have made progress in the brain. Yes, we do understand, but it's one thing to understand how an earthquake works, and it's another thing trying to stop it or to predict it. We cannot predict it, and yet we know how the earthquake deeply works and lasts. So I would be very, very, I would say, not ready to make any general conclusions about it. We have made a start. And it's very beautiful that in the arts, when you see a painting, for example, of a tree or a painting by Pollock, as you know, there are fractal, and I have spoken about this in the past, fractal structures in a painting. And then you begin to wonder, why? Is fractality beautiful, maybe? I don't know. But I feel a beauty. I feel a sense of happiness when I see it. So there must be something in this piecewise operation that the brain chooses to perform. It's either a task to follow the tapping of a finger, or it is a dream. And they are not easy to understand. I was very interested in the talk that we heard. It makes some parallels between beauty in the picture and beauty in the music.
Thank you so much.
Yes.
So now I see Navid and then Rushmir and Huiyu. First, please, Navid.
Thank you, Violeta. Wonderful, wonderful talks. I'd like to thank both speakers. I have a few comments for Aziz. I very much enjoyed, your talk. A great presentation, wonderful examples. Just for the sake of clarification, I wanted to bring up a few points. You correctly mentioned the 11th harmonic as, a particular harmonic that gets really close to a quarter tone with 49 cents difference, with the ratio 11 to 8 between C and sort of like 49 cents narrower than, the tritone or tritonus on the piano. I just wanted to say that in the just intonation or pure natural tuning theory, we call that usually just tritone, as opposed to perfect fourth, because perfect fourth, we already have that between fourth and third harmonic with the ratio 4 to 3. That's just the arbitrary designation I wanted to bring up. It's usually called just tritone and not just perfect fourth. The other thing I wanted to mention about Persian music was that you mentioned the concept of dastgah, which is somewhat different than makam in Arabic and Turkish music, for instance. The makam is more or less similar to mode, like let's say the church modes, the diatonic church modes that we have in the West, whereas dastgah is essentially a collection of short pieces, like short musical pieces, short melodies. Each of them are in different, maqams or different modes, and we modulate between them when we are, let's say, in dastgah chahargah or dastgah nava and so forth. So it's based on the concept of maqam, but to a certain extent different than that. The other thing was the idea of intervals in the Persian music. And you are absolutely right. So many authors, theorists have written about quarter tones in the Persian music. But what is true is that we really do not have quarter tone interval in Persian music. It does not occur. The two intervals that occur that are sort of close to quarter tones are an interval of 135 cents and the other one 160 cents, as opposed to quarter tone, which is, you know, like 50 cents smaller than, you know, a whole tone, 200 cents. But a quarter tone, in the true sense of the word, it does not really occur in Persian music. And the last thing, again, very nicely, you mentioned Vishnegradsky's text, where he theorized, you know, a harmony system based on extended 24-tone to octave equal temperament. I just also wanted to mention that Alois Chabad, that you also mentioned, has this book in German, Harmonie Lehre, which was republished, if I'm not mistaken, in 2006 or 7 by the German musicologist Horst Peter Hesse. For a long time, he was a professor at Mozarteum in Salzburg in Austria. And there he also sort of systematically theorizes a harmonic system.
Excuse me, Navid, do you have a question also?
No, I don't. And this is my last sentence.
No?
May I finish that, or should I stop?
Yeah, of course. But
Okay.
I was thinking you had also questioned something.
No. I just had a few
Okay.
comments because they were really great points that Aziz brought up. I just wanted to say that this book is republished and now available. For a long time it was not, and there he theorizes all the way from 12-tone equal temperament harmony system through 24-tone up to 72-tone to octave extended equal temperament in this book. Thank you so much for the great presentation. Sorry, Violeta, for too long.
Thank you, Navid. Thank you so much. There's a very endless discussion. There are so hundreds of maqams. So the incredible cosmical world. Thank you so much. So now I see Rusmir.
Can I add a comment, just brief comment?
Please, please, Aziz. Thank you.
Thank you. Thank you, Navid, for your comment. You're right. So there is debate even in the Arabic world about this equal temperament, and even in Persian music, some theorists, they say that it's more close to the 70th tuning that was introduced by Safiuddin Armawi. And in Arabic music, there was the first Congress was in Cairo in 1932, and there was a very important point in discussion. It's about equal temperament. Shall we adopt it or no? This was the point. And some theorists, they rejected this equal temperament because they claim that in Arabic music we don't have quarter tones. We have, for example, 3 quarter tones. We don't have quarter tone in any maqam. And also they claim that that equal temperament does not reflect the reality of maqams. For example, when you play E half flat in Rast, it's slightly different from E half flat in Bayati, for example. And like in Western music, they argue that if we use equal temperament, we lose some pure intervals, like the pure fifth or the pure fourth. So we have in Arabic world the same debate that was in Western music about equal temperament and just intonation. Yeah, thank you.
Thank you very much. Please, Rusmir.
Thank you so much. My cordial greetings to everybody, and thank you so much for these moving presentations. I have a question. Aziz was speaking predominantly on instrumental music, and mathematization of instrumental music is one thing, but mathematization of vocal music is different things. In the world from which this music presented by Aziz, vocal music as sacred art, as liturgical art, has high position in the art of music. Eastern liturgy without instrumental music, chanting sacred texts are essentially the highest possibility in sacred music. I ask Aziz, what about the relation between sacred liturgical art, especially developed just in this world, Arabic, Kurdish, Turkish, Iranian, and so on, under, let's say, taking the revealed text, sacred text, as the most beautiful human possibility. Thank you.
Indeed, it's wonderful. Thank you very much. Now I see, I saw who you, please.
Okay. Okay. Yeah, thank you. Thank you. This is a great presentation. I just have a question. Not really question, the comments or some information for the Aziz, because actually this is the quote note. It's Klaus Mann mentioned that the culture contact. I don't know if you realize that even in China, very close to Central Asia, in the close to the Muslim area. It's not in the Muslim area. It's still in the Han Chinese area. There's a note. There's a scale. Actually, there's only one note very close to the quote note. We call it the 3/4 note, and there's only one interval. Just one interval. Nothing else. Everything is Pythagorean tuning, all the 12 equal terms, just one interval. And this, I think, is from the Central Asia. So this is related to the cultural contact. The other issue I want to mention is that you, in the last sentence, you said that the quote note is natural. But the problem is that actually all of the equal temperament systems are not natural, are not pure. All pure system, all pure intervals are not natural. I don't know if you realize that, because whenever we talk about Pythagorean tuning, talking about the just intonation, they cannot be closed. There are always something called a comma. You mentioned that Pythagorean comma is 23 cents, and the other comma, you said the quote note, the other circle of fourth, there's another comma. They cannot be closed, but they are pure. They are really pure. So this is a very, very, very difficult situation. Actually, it's very related to a philosophical discussion. I recently read a book by what's his name? I forgot. This is very philosophical situation. When we want to close the comma, we lost the pure music. We want to get the pure. We lost the modulation. Actually, I also found that even in the gamelan music, there are some intervals also from the harmonic series. So this is maybe open to the academic debate in the future. But I'm very glad to hear you're talking about this very interesting topic. Anyway, thank you very much. All right.
Oh, thank you also very much. I wanted to tell you that here I just wrote me Rami Shahin, that he is here. Rami Shahin, are you here? Can you?
Yeah, can you hear me?
Okay, please.
Yeah, okay, thank you very much. I appreciate it. I think many thanks for both people who spoke in, both lectures. And I find also a very strong relationship between both lectures for today. Because now talking about overtone, so it's starting from fundamental tone and going up, and then we can find from each overtone another fundamental tone and going also up and finding another overtone fundamental from a fundamental. So there is a connection, a strong connection. And now talking about Arabic music, I think in 1932 in the Congress, in the Arab Congress for Arab Music, there were a big mistake when they described Arabic music with a quarter tone, because Arabic music is not based on quarter tone. It's based on overtone series. Quarter tone, it's more to be mathematical, logarithmic, and overtone, it's related to the overtone series, which is started with one half, 2/3, 3/4, and etc. So in this case, the harmonic sounds, it would be very different. So when we talk about, for example, 50 cents, or for example, like F quarter tone, it's different from logarithmic F quarter tone. It's very much different from the F 50 or not 50 cents, actually, the logarithmic or the overtone F. So in this case, even if we are talking about Persian music, Indian music, I mean, even for example, like in most of traditional music in Japan, also, I analyzed many pieces, and most of the work, whether it's in traditional way it's tuned or based on overtone series. And one of the oldest tuning systems is the Babylonian overtone, the Babylonian tuning system, which is what we call it now Pythagorean tuning system. And it's something like 5,000 years old tuning system. And it's based on the overtone series, where they tune the strings depending on the half or the third of the length of the string. So each string is tuned based on different, the first string.
Thank you, Rami. Thank you. This is also the beginning of a new area. It's very interesting, and I hope you shall communicate later. I received from Annette Kerkhoff. Please, Annette.
Yes, well, thank you for the wonderful talks, both of you, and to Aziz. I didn't listen so academically to your talk, but very emotional, and the kind of the correlation between the sound and the emotion. And I felt, as I wrote in the chat, that the quarter tones can mirror emotions with which the half tones cannot. And I'm very interested in jazz and blues, so I feel that you can find some emotions which are mainly there. Also, how you don't sing in steps always, like not like a staircase. But I once went to last Sunday, I went to a klezmer concert with Syrian music and Oriental music. So I find in the Western music sometimes we miss something, having only half tones. So that is the reason why I wanted to thank you and think there are a big correlation between these emotions in different Western American, Arab, Oriental, Maghreb, whatever music. And that could also be an emotion.
Thank you very much. I hope that Rami Shahin also speak about his music. Now I see Adalbert Grote. Adalbert Grote, please. You wanted to say something?
Yes, my question goes primarily to Aziz, to the last speaker. He has made a disposition about the European tone system and the Arabian tone system. And in the European tone system, the relationship between theory and practice is, at least until the Renaissance music, very close. And I would like to know, I would like to know how close is the level of the theory to make the tones, or to explain the tones and the height of the tones. How close is that connected to the practice? How close is the theory connected to the practice? Is that comparable to the Western kind of handling the music, or is that different?
Can I speak?
Yes, please.
Yeah. Thank you very much. In fact, I will say in North Africa and the Middle East, actually most of the music we listen, it's equal temperament, 24 equal temperament or 12 tone equal temperament, because we use electric instruments, and most of electric instruments equal temperament. But when we use violin or lute, the most popular instruments in Arabic world, we can use other intervals that we don't find in equal temperament. But in practice, the equal temperament, even there is no consensus between theories about this equal temperament, but in practice it wins. Here we have a real debate, because those who say we need to adopt equal temperament, they have their arguments. They say that it's practical, the theory becomes more easy, and we can construct instruments, and we can transpose. There is no limitation to transpose. The other theorists, they say that equal temperament, it's not pure, it does not reflect our music. We have slight differences between pitches, but the major problem with all those let's say natural tunings is that transposition is limited. Mathematically, we can prove that the only tuning system that permits all the transpositions is equal temperament. Outside equal temperament, we are limited. And so we have two choices. No one of them is perfect. When we win some things, we lose other things. So it's not easy to choose. Huh? That's why it's topic of debate. Yeah.
Thank you very much.
You're welcome.
Thank you. Also, I just communicated shortly with Rami Shahin. I just wanted to, I hope that you shall take contact with each other, because Rami Shahin made a doctoral work and also composed and had the idea to create his own makam in order to create also harmonical structures. That means Mehrstimmigkeit, several voices on the vertical, from the vertical point of view. So for an essence of melodical old tradition, because it's also very interesting. I'm coming from Romania, and in Romania the traditional music has a melodic dimension. There is also the harmony, of course, but there is a melodic dimension, which is also in connection with narrative dimension, which is characteristic, very strong characteristic of makam music. So, and on the other hand, you showed us so nice how makam are looking, but in fact there is a way of using the pitches. I mean, when you are recognizing a makam, it's not enough to see only the notes, but you have to feel the life of these notes. Anyway, it is possible to see the connection between these two lectures today, because what Tassos Bountis presented is something very deep in connection with musical way of thinking and structures. Yes. And your comments, Tassos, about the how is it possible to communicate between very, very strong intellectual way of understanding the world and intuitive way of using. And in fact, this connection with a way of the definition of makam. You have a structure which is so mathematical constructed, but on the other hand, you have the intuition who is just opening a totally different way of feeling and thinking. So
yes, you
it's
see,
a mystery, and it's so wonderful. Tassos, you said we do not understand. It's wonderful. You say we do not. We can do so many things, but finally we do not.
Yes, but it's you see the content of my talk was more visual and not so relying on feelings. There in music, even when you speak about structures and the Pythagorean and Indian and Arabic versions, then the important ingredient is feeling, sentiment. What does it? You used often the word. It sounds beautiful. It is more harmonic. These are very subjective, I would say, arguments, and you can continue to discuss for many years. And the point with art is not to decide something, because it's up to the listener to get the more subtle feelings behind it. See, so mathematics is there in the form of Pythagorean structures and all the integers that are used, the ratios between the different tones. But in nature, life is more, I would say, visual and more intellectual. And we can find laws and rules. In music, it's difficult to describe things through laws and rules. You see, the subjective comes into it, of course. But at least you saw a similarity between my lecture and the one by Aziz, is that there is a basic structure. We begin with something that is the foundation of what we want to build. And if you want to build a tree, well, then we will go on to the branches and the leaves and understand something about its structure. But when you build a song or a music like or a symphony, for example, then you start to have different interpretations according to how people listen to it, what they feel about it. Then we're out of science. Then we are into arts. Completely. So there was a relation between the two talks. I appreciate that, but we had a different point of view.
Thank you very much. You know, I don't know if Yu is still here because I do not see him. He wrote me, I think blue note is nature, but the 24 equal temperament needs to be artificial. As there should not. Are you here, Yu? Oh, yeah, excuse me. I didn't know.
Not for you. I'm just thinking about this because there's some confusion. I think I want to clear about it. That's my
but you didn't mean artificial. You meant artistic, maybe.
Yeah. It's not really natural. When we're talking about equally, we must actually mathematically divided without any comma. So if there's a comma existed, we cannot call it equal because the chord notes, according to harmonic series, that is 49 cents, not 50 cents. So the natural one is 49 cents. The equal temperament one is 50 cents. So that's a difference. So there's something pure, something not pure. So that's my thinking about it. So it's not important. Thank you, Violeta.
I thank you very much. So it's wonderful that we had the feeling that we can continue, but now it's very late. I would like to ask you if I missed somebody. No. There is another question or comment.
We are quite late. You are right.
Okay, so Dušan, thank you very much. And now we ask Klaus.
Oh.
Again, please, Claude.
Yes, but I will only give a very short comment. Let me pick up the term which was highlighted by Tassos, namely synchronization in the brain. And to make a long story short, it seems to be and is obvious that there is a lot of disharmony in the world and hostile behavior. And on the other side, in mathematics and in music, we have all these wonderful common language to communicate with one another. So I think what we should consider in the future, and I remember Annette Kirchhoff underlines this point too, namely the connection of these disharmonies and synchronizations with our feeling. And I think that would our emotions, that would be a strong request for further research in the future. How can we arrange that this kind of synchronization and harmony is realized even in the political world? Thank you so much.
Oh, it's wonderful, but I also would tell you also something about the piece of Ligeti with hundreds of metronomes. But he didn't have this idea to put them synchronizing at the very end. They were just stopping somewhere, and it was a perdendosi disappearing. So thank you very much again. And
Thank you.
I hope
Thank you.
Thank you and goodbye.